So I want to finally move on to talk about transformations that we could do on these geometries. So the three main transformations that you usually want to do when you do graphics are these. First one is translation. It means taking an object and move it in 3D space while maintaining its shape. Rotation. This should be fairly obvious what it is. And scale. And in here we're just going to talk about uniform scale. There. And I've copied the ambient occlusion code from our last video, and we're going to do the transformations on the scene that we already have here. So, transformation, how do we transform a sphere? Now remember that we obtain the intersection results by repeatedly feeding the point that we're testing into a signed distance field function, right? So in other words, P represents the space in which the ray is traveling through. And if we transform space, then we kind of transform where the where the shape is if we get the camera fixed, right? So think of it like this. If somehow you're fixed in the elevator and there's a camera attached to the elevator, right? If the elevator moves down while you somehow maintain in a fixed position, then kind of, let me just draw it in here, then it'll become this is a new elevator. You know, it's still fixed with the elevator's frame of reference. You're going up, but we're still, you know, all we did was transforming the space down, and in the transformed space perspective, the object that stayed fixed went up. So whatever transformation we apply to point, the inverse of that transformation will be applied to the shape that we're trying to render in this case. So let's test it out. Let's test it out. If we want to transform P, so let's say we, this is a sphere we have, right? What we want to do is to push it up so it's finally separate from the ground plane. What we want to do is to move it up by 1, right? And in order to do that, we have to do the inverse of that transformation on the point that we're sampling. So in this case, we'll be adding, you know, the negative one. We're trying to pull this, we're pulling the space down, and in which way we're basically pulling the shape up with the frame of reference to the camera. So if we do this, we pulled it up, right? And a more elegant way to write this, well, more intuitive way, is to just put the translation vector here and have a subtraction instead of, you know, addition. And it looks kind of weird because our camera was still pointing at where the sphere was. So let's just move it up. Since right now it's at the y equals 1, and let's move the camera up a bit. I guess we can do 2 now, right? All right, let's move it back a little bit just so it doesn't look too weird. All right, so I guess I'll do 1.5 or something. Okay. 1.4 looks good. All right. And I kind of want to see the front face of it instead of staring at the shadow since we're done testing that. So let's see. I think we'll do. And you're going to notice some artifact right away. Okay. But do not fret. These are due to the fact that the shadow is too soft, so there's too much error allowed in the computation. If we just move this up a bit, right, so it's some acceptable value. You also see the color kind of, in here the color kind of reached its intensity, so you can think of it as all the color channels are going through the upper bound, which is 1, but then they just clump together because it gets clamped in the way. So the reason of that is because we don't have a way of doing high dynamic lighting yet, which I will talk about in the series, or not be in this video. So right now the problem is if we get full indirect lighting and get full direct lighting, the sum of them will be 1.2, so there will be a portion of the area that gets lit equally because, you know, our lighting gets clamped to both 1. So a simple fix will be limit the amount of direct light you can get. So always multiply 0.7 to the direct light. Therefore, you cannot possibly have a value that's over 1, and therefore there won't be an area in the scene where the light are the same value. All right, so let's save that. Actually, why don't we try to spin around? In idle position, it's kind of boring. So remember your unit circles. It's just sine and cosine. So we want to rotate it in the xz plane while fixating on the same y, right? Okay, it's I time, and we're spinning inside a circle, kind of. I mean, inside a sphere. And what we want to do is try to push it out a little bit, right? And unfortunately, if we do this term here, we're also multiplying with the 1.5, so why don't we distribute the scale back into x and z component? It's out of here, and there we go. Spinning at a relative fast pace, so let's get an intermediate time variable so that we can control the pace of the camera rotation a bit more. This way, it can kind of just look at each part of the lighting for free and see if they're behaving the way we expect them to behave. So we got a sphere and we've got down how to transform space. What's next? It's rotation, right? Well, rotation is something I kind of want to defer till later because I want to introduce quaternion, which is a way more superior way of representing rotation in 3D space. But if I do in this one, then the video will get too long. So I want to focus on scale next, because scale is tricky, actually. So following what we said, right, we want to transform the space inversely to have the desired transformation impact on the geometry. So if we want to scale this geometry by s, say we want to multiply the scale of the geometry by s, so you multiply the inverse of s, right? That way you kind of expand everything out a bit. However, this is kind of let me just show you. How about I just show you? So say I want to scale a sphere, I want to scale it by 1.5 amount, and this is the transformation that I did. And now I want to multiply by the inverse of the scale that I have. Right? It's going to get bigger, but it will break. I guarantee you, this is not the correct STF function for this for the sphere. Believe me when I say that, because let's try to get far away. I'm just gonna make an intermediate variable called camd as camera distance. It's not really the distance, but it's the relation to it. So say we wanna let's try to increase the scale a bit. Then it will break. Okay, I guess sphere is kind of a interesting case here because it will not break, but take my word for it, it's not the correct transformation. The reason for that is, so imagine we draw grid lines, just to show the space before distortion. Okay, so these are one unit grid. This is our sphere. When we scale it by s, we've expanded the sphere, but we've also expanded the grid line, which is essential to having accurate distance estimation. So what we want to do is post scaling the thing after we get the distance function. I want to multiply by s again. Do we really want to apply by s? I am not sure. I think, yeah. If we multiply by s, then we're gonna get, then we kind of inversely transform it again without touching the shape. So it's just gonna be equally as big, but then the grid line. So it would be the space where ray is traversing, be as granular as before. So we actually have a bigger sphere in this case. So let me just multiply s. I don't think anything will change, but okay. Actually, there is one artifact. Is there though? There could be. Let's look down a little bit just to show you. So okay, you see how, huh? I mean that could be correct. Okay, I think I guess it's correct. Whatever. So if you apply S back, what just happened? Oh, I forgot this. Since this is part of the SDF, have to multiply S to everything, so all of it. So in this case, there won't be much of a difference, but trust me on that. There'll be problem with scaling if you're not careful with this constant that you have to multiply outside of it. When we see more concave shapes, you will see that happening. All right. So that's the scaling part. Now, you might have noticed that we have transformations and CSG in both in the title. Right? What the hell is CSG? CSG stands for Constructive Solid Geometry, which we already encountered, believe it or not. I just chose not to tell you straight away. So you see the min here? That's one of the essential CSG operations. This is called union. Union means I'm combining the shape into one single shape. There's union, there's intersection. They create very interesting shapes. And I believe there's intersection, union, and what? And difference. So I'm gonna excuse me. So there are websites that explain these three things way better than I have. Whatever, do the job. One of those websites is called Scratch Pixel, and in here they kind of explain what each of these operations are. Right? Feel free to prove all of these yourself or get an intuition for it. I will tell you my way of understanding it. So for union, taking a minimal of D1 and D2, that's pretty obvious, right? Because you want the minimal distance. Therefore, you kind of taking the maximum outline of the shape because you're kind of being very conservative to what distance you choose. And subtract, I like to think of subtraction, which is the difference here, as a result of applying an intersection. So intersection, interestingly, so if there's a sphere, there's a rectangle, then it returns you this, this intersection of the two spaces. So max D1, D2, the way you think about that is when you take any point in space, right, say the max only gives the proper distance estimation if the two shapes overlap. So it's only valid if they literally have the same two values here, because only during intersection they do not care. And anywhere that's outside of these shapes, there's bound to be one of the shape that has a positive value, even though you're inside one of the negative spaces of one of the geometries. The other geometry will treat it as positive space, and therefore this max will always return a positive value for the sine distance function. What does the positive distance mean? It means it's far away from the object, therefore the intersection only gets taken care of. Subtraction, it's also a max operation, but I like to think of it as the intersection of the negative space of the first geometry with the second geometry. So the sphere in this case is the first geometry. If you negate it, then you kind of have this shape of the infinite 3D shape that takes up the entire space except the little sphere in the middle, which is carved out, right? That's what it means if we inverse it. And by taking, the inverse of this thing with the space with the rectangle, you can obviously see that the rectangle's overlapping region is this area. So that's the returning area. That's how I use intersection. That's my intuition for union, intersection, and subtract. I feel like they're pretty intuitive. So that's the constructive solid geometry. Another website I want to introduce to you is IQ's website. IQ is the guy who popularized this method of rendering and box, and he has a ton of useful functions that you can treat them as games by proving them, try to prove them yourself. It's very fun and it's very useful, of course, when you're not up to the task. So let me give you actually one thing to note though is that these constructive solid geometry operations were not they have the assumption that the function you feed into them is signed. You see how it takes advantage of the fact that some of the geometries, the negative space, the positive space, it takes advantage of that. And if your function is unsigned, then even if we do this operation with these, this, let's say this side is this function, it will not work because it's not signed. If we want to introduce a box into our scene, it better be signed, right? So actually, unsigned operation only stops working when it probably stops working with intersection and subtract, and still works with union just fine. Just for information. So let's copy the distance box, sign distance function to the box. Let's copy it up here. It's all written in GLSL, which compiles immediately. So sphere SDF, what do we want to do to it? Actually, let me just remove the scale since we're done with that already. It's very painful to not be able to edit in my own text editor, because this will be done in a second without the use of mouse, but I should have a tool for that so they can use your editor. But now it's not the time to introduce it. Sphere SDF, we can do what do you want to do? I guess we could do an intersection of the sphere and the box. I think the result will be pretty interesting. So let me get the camera back at a good angle. Look at the geometry, and so SDF is equal to, this is no longer the sphere, since we're going to do some operation on it. So we're going to rename the sphere to obj as the object of whatever we're rendering. So let's try max SD box. The position again, do the same transformation on the space. The second operator to the function is, I assume it's the dimension of the box, which is just going to be 1, and max with the obj SDF itself. Okay, let's put this in front of it, just so we imply that we're appending this geometry to the geometry we're having with the given operation. Okay, is this the intersection? Okay, so I think maybe the box is a little bit too big. There you go. See, there we go. That's something. So what happened here is that the box is kind of laid out. Let me just show you. Let me show you what the box is, so you can get a better sense of, you know what? Actually, this is a really bad way to do it, but actually, it's I'm trying to make it written in a better form of code. So obj would just, SDF would just be the sphere SDF. God, I hate this thing. Box. I don't usually do graphic stuff in shader tool. I do it in my own tool. So I'm not used to this. Okay, declare more. All right. So if I just put box SDF here. So this is the box, right? This is the box function we imported. Let's look at the ambient occlusion. Actually, that's interesting. This actually looks really good. A little banding that I reckon you could fix by yourself just by tweaking the ambient occlusion parameters. So this is a sphere, right? You can see how the intersection of them can form this shape. That should be quite intuitive, right? Right. So this is already interesting. So what if I take a negative space with the sphere? And we get something like this. Just wow, cool. Something's wrong with whatever's inside because there's something else that we need to talk about. Sometimes if you do operations with these things, the result geometry might not be a true distance functions anymore, since the positive values might be too big. But nonetheless, it's an interesting shape though. So what we're gonna do is, this is the hack. So what we do is try to multiply it by some small constant to make the distance functions to step more carefully. Oh man. This works really well, but this doesn't want to work. I guess part of the reason, you see, it's a little bit tweaking in this aspect, so if I increase this a little bit, it doesn't help. But that's the shadow. How does a shadow have so much impact on that? Whatever. If I increase this thing, okay, there we go. This is just I've increased the. It might be because there's more stepping that's required due to the nature of the operation we're doing. So you kind of see I'm tweaking these things. You can probably get these intuitions with your experience, I guess. So you don't have to worry about that. If I do this thing, okay. Okay, so this is the geometry, which I think is very interesting, right? And combined with your, there's some artifact in the shadows. I reckon you can fix them, and combined with the shading we have, the shadow and the ambient occlusion effect on the bottom, this looks quite interesting and pleasing. With a weird artifact, you can argue that it's ours, right? Okay, so I guess one last trick I have. You know what? Never mind about that. Last thing I'm actually going to say is IQ's website, besides all his fantastic sine distance functions to different kind of geometries, he also has code for different, operations, as the rotation translation scale, which he does, the same thing here, and the repetition. Oh yeah, this is fun. I will leave it to you. In the meantime, though, I'll show you what it does. OP wrap, assign distance. Whoa. Is he really? Wait. What is that? Can you pass in functions in GLSL? Because that's something that's new to me. Why don't we try? No, you can't. I guess it's just the notation he's using. Well, whatever. So OP, I'm going to move current point. So it's just the point that's getting transformed. All right. So OP wrap. I'm going to try to do it on our geometry. Right. So P equals OP wrap repetition of the point, and this is kind of the isolation domain. So if this is 1 by 1 by 1, then each repeated geometry will have 1 in between them. So okay, some of the geometry is blocking our camera. try to tweak it a little bit. Oh God, what am I seeing? You know what? Okay. I'm just gonna move the camera up a bit. So I suspect it has something to do with. Okay, guess not. Okay, guess not. Um, this is fun. So what if I don't have anything? Okay, just a slight bit of it. Oh, give me a minute. Okay, so I think I got it. So I'm not gonna use this function, right? Instead, I'm just gonna do the operation on the XZ plane. So I'm only infinitely repeating this geometry on the XZ plane. Therefore, there won't be different weird Y stuff on the outside. So p dot xyz, this is just gonna be I wonder if mod operator takes like a single thing. So let me one be the distance away from them, which is not good actually. Let's just see what it does. Okay. Let's see. Let's make it back 2. So wow, interesting. So there you go. It infinitely repeats stuff. That's what the function does. Let me just lift it up a bit. There you go. You can almost, sense that you cannot possibly do this in a traditional rasterization style, right? This is something that's unique to the procedural world, as all geometries are represented by functions. You can do all kinds of funky stuff to functions. Just so, like infinite repetition, it's really interesting, let me tell you. Really fun to do this, kind of stuff, to experiment with yourself and try to discover some new rules to the game. Wow, just stare at it. And there's literally an infinite amount of cubes everywhere I walk. Just to give you, just to give a sense of the distance, we can try to add distance fog, which is just a simple interpolation between the current color and 0 by feeding it. What the hell? Tmax. We have Tmax or a capitalized Tmax. Where's my intersect routine? So we don't have any Tmax. Well, interesting. I'm just gonna put some number here. Right. Okay, there you go. So this is the basic distance fog that we have, which is not really good because the fog is doing the thing linearly, and if we do HDR and try to actually gamma correct the colors here, we will actually get a very bad, it's even really close to camera, it still gets dark really quickly. So one of the trick we can apply is to apply the power function, give it a quick exponent, so that, well, this might break this though. It might break. Okay, never mind. So here we go. There's some fog in the distance, and it was like some real scene, I guess. I still don't like how clustered they are. I don't want to be so clustered. So maybe 9. Oh god. Or we can make this term animate, right? I want them to touch at the end of the animation. So how do I do that? 2? No, that's too much. I think it's 1.5 or something like that. No, it's 2. Let's try 2. So it's much 2.5. Probably 2.5 will work. Okay, there we go. So you can obviously see that you can create some crazy random dungeon out of this thing. You can see when they converge, it kind of form some kind of cave system. You can do crazy stuff with it. You can increase it in the Z in the Y dimension so that you can traverse in some kind of cave. There's shaders you can already look at that does this. So let me just double check if I've done everything that I want to cover in this video. Right. I was thinking that the camera's spinning too fast. And all right, I think this is very good speed for this. And you can see the rendering time has not slowed down even if we're adding literally infinite amount of geometry. That's because the ray stepping procedure dictates how fast the performance is, and by adding more geometry to it, there's still only a finite amount of computations the ray has to do to get the distance. So we have a distance function to an infinite amount of geometry, which is really cool. And we can see more of that when we introduce fractals and infinite details and stuff. So I guess I'll leave this video at this, and I guess we'll see you next time.